Hello, welcome to this lesson tutorial. So in our circle lab, we took a meter stick or a ruler and a piece of string, and we found 8 circular objects. We measured the diameter, which is the distance across, and we measured the circumference around using the string. So we wrapped the string around the object, and then we unwrapped it and measured the distance from one thumb to the other as our measured circumference. And so in our data table, we took data for the diameter and circumference of 8 circular objects. Now, what I'm going to do here in this tutorial is I'm going to walk you through how to construct the graph, how to process the data, and how to ultimately make sense of it. All right, let's begin. I'm going to work with some sample data that I have. You try and do this with your own data. Okay, so let me go ahead and mark off my work here. So I have, let's see, 4.8, 15. Let's see, 11.4 and 31 and a half. Let's see, 3.8, 14.9, 2.5, let's see, 8.8, 1.9 and 6.9, 2.6 and 9.2, 12 and a half and 41 and a half, 3.4 and 11.5. Okay, so what we're going to do is, using this data, we're going to use the steps below, written down below, to come up with the range of your data, which is going to go from 0 to a number slightly higher than your largest data point. Then we're going to figure out and choose a scale, what numbers we want to go by. And then finally, we're going to choose the number of interval boxes we're going to skip to get there. Okay, so let's go down and take a look at those directions below. Okay, now the first thing we're actually going to do is we're going to come up with a title. Well, the title is always written as the dependent variable on the y-axis versus the independent variable on the x-axis. So we are plotting, in this case, the dependent variable was the circumference. Circumference, in other words, depends on how wide the circle is. That means the independent variable would be diameter. Okay, both of them in centimeters. So my title would be circumference versus diameter. Well, on my graph, I need to label these axes. So for the y-axis, I'm going to label that circumference. Now, I could write out the word circumference if I want, or I could use the letter C, which is the variable for circumference, and I need to make sure that I write the appropriate unit that goes with it. Okay, and then same thing on the x-axis. D for diameter, also in centimeters. So my first steps, 1 and 2, are title the axes, label both axes with their units. Okay, big deal. All right, now is where we got to actually scale the axes so we can estimate plot points. Okay, so first step, find a range. It's going to go 0 to a number slightly higher than the largest data point. So first thing I'm going to do is I'm going to find the largest data point for each one, and I'm going to circle that. Well, that to me looks like this right here. So I'll go ahead and highlight this. That is my largest circumference and my largest diameter. What that means is I'm on the x-axis, I'm going to go to a number slightly larger than 12 and a half, 13, 14, 15 maybe. On the y-axis for circumference, I'm going to go slightly larger than 41 and a half, 42, 43, 44, 44, 45, maybe 50. We're not going to go super high, and we're definitely not going to be below that, but you're going to a number slightly higher than that largest data. Well, then we need to kind of count boxes on that axes to figure out what scale and interval you want to go by. The scale, well, that's the numbers you go by, right? You could go by 1s, 2s, 0.5s, could go by 10s, could go by 20s. What number are you going to go by? And the interval, well, that's how many boxes you skip in order to get to the top part of the range, okay? So let's take a look at the x-axis first. My largest value is 12.5. So let's figure out how many boxes we have. So there's 1, 2, 3, 4, 5, 8, 9, 10, 11, 12, 13, 14, 15, 20, 21, 22, 23, 30, 31. Okay, so I count 46 boxes across, okay? And then going up, $30 boxes going up. Okay, so we got 30 going up, we have 46 going across. So what I'm thinking is we really have to kind of spread this out a little bit, okay? What I mean by that is I need to go to about 13. Well, what I'm not gonna do is I'm not gonna go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, because then all my graph is gonna be right here. That's pretty small. You want to extend this out as much as possible, okay? And the way we do that is by lengthening our interval, skipping boxes basically. So what if I, let's say, doubled it? Well, every 2 boxes would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, right? 14, 15. And that's not bad because it goes a little more than half of the graph. So if you can extend it at least a little more than half the graph, then you're giving yourself a good graph to work with. Okay, so I'm going to go ahead and work with this data right here where my interval, my scale is going by 1s, but my interval I chose to skip 2 boxes for every one. So every 2 boxes is 1 centimeter, right? That's my scale. Now my vertical scale for circumference, I got to go up to about 41.5, but there's only 30 boxes to get there. So I can't go by 1s because there's not enough room. I may have to go, each box is 2. So I'm going to scale it kind of like this. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, 42, 44, 46, 48, 50. Okay, so 20 would be about, 20 would be about right there. Right there. Okay, so my scale on my vertical scale on the y-axis in this case would be every box is 2 centimeters, whereas my horizontal scale on the x-axis is every 2 boxes is 1 centimeter. Okay, so we got to come up with our scale first. And once we come up with our scale, then it's about estimating plot points. Right now, pause the video, create your x-axis scale, your y-axis scale that matches your data, then take a moment to plot your data points. All right, so now that you've had a chance to come up with your scale and plot your data points, let me go ahead and do the same with mine, and we'll go ahead and move on to the next section, which is called Best Fit Line Construction and Analysis. So let's go ahead and do this. I'm going to be going almost 5 over and 15 up. So 4.8 would be halfway, and then 15 up would be exactly halfway. That means the first dot is about right there. And then I'm going to go 11.5 over, 31.5 up. So let's see, that's 11.5 over. 30 is right here. 32, that means 31.5 is right below it. All right, she's estimating her plot points, right? Okay, so then we're going to go on almost 4 over and almost 15 up. About right right there. Then I'm going, let's see, 2.5 over and almost 9 up. Put it about right there. Okay, then I'm going almost 2 over, 1.9 over, and almost 7 up. Okay, then I'm going 2.5, 2.6 is pretty close to 2.5 over, a little over 9 up. That puts it right there. Pretty much right on top of that other data point. And then I'm going 12.5 over and 41.5 up. So 12.5 here, 41.5. Well, that would be 42. 41.5 would be right below it. That's 41, sorry. 41.5 would be about right there. Okay, and then I'm gonna go 3.4, about 3.5 over, and 11.5 up. So that would put it right there. Okay, now you can see we have a lot of points that are basically very linear. This to me looks like an outlier that's slightly off the path. So now what we're gonna do is we're gonna create a best fit line. Well, best fit lines, number one, do not connect the data points. We don't do that. Okay, so don't connect the data points. Don't simply connect the first point to the last point. That's not always a best fit line. And don't try and force it through the origin 0, 0. Doesn't have to do that. It'll get very close most often, but it doesn't have to go through the origin. What you're gonna do is you're gonna set up your ruler so that you are following the trend of your data. And when you do so, you'll see in this case, the majority of the data points look just like this. And you can see there's an evenness and there's a balance. Some points are on the line, some points are above the line, some points are below the line. Okay, that is what's called construction of a best fit line. So make a best fit line. Everybody take a moment, pause the video, and do that with your data. Okay, so again, just a reminder, we never freehand a best fit line, always use a straight edge, a ruler to make that happen, okay? Now, in our next section, we are going to calculate the slope of the best fit line and then finally determine its physical meaning. So we're at the tail end, we're almost done, okay? How do we do this? Well, we're gonna start at the bottom end of the best fit line and we are looking for 2 locations. I'm gonna circle them in blue. 2 locations, kind of like this right here, where the best fit line itself, not the data points, but the best fit line itself. In fact, I'm gonna make the best fit line a different color so we can see it more bold. Okay, now I am going to circle 2 locations. Okay, you guys all see this box right here? Well, your best fit line is going through the upper right-hand corner of that box. So I'm gonna circle that location there. And I'm gonna keep going up the line until I find another location. That's not too bad. I think I can do better. Yep, there we go, right there. So that box right there, you can see how the best fit line is going through the upper right-hand corner of that box, okay? Now what we do is we make a slope triangle that goes from one box up to the other. So it's going up and it's going over, just like that. Okay, now in 7th grade, when you learned how to do slope rise over run for the first time, you simply counted boxes up and counted boxes over and then divided them, rise divided by run. Well, it's similar to that, but your scales aren't the same. So we can't just simply divide rise by run. We have to take the rise according to our scale and then the run according to our scale. Here's what I mean by that. You have 1, 2, 3, 4, 5, 6, 7, 8 boxes going up on your rise according to the slope triangle. Well, 8 boxes according to your scale would be 2, 4, 6, 8, 10, 12, 14, 16. That means your rise is 16. Your run, well, every 2 boxes was 1, so we're gonna count the boxes first. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But what is 10 boxes on your scale? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That would be 5 centimeters. So your run is 5 centimeters. All right, now finally, on your graph, what we're gonna do is we're gonna go ahead and calculate the slope. So the slope, right, it's rise over run, just like it always has been. But in this case, we're gonna go ahead and put in our rise. In this case, I got a rise of 16, and I got a run of 5. Okay, rise 16, run of 5. And I'm gonna go ahead and estimate that slope with a calculator. Putting that in our calculator, 16 divided by 5 gives me about 3.2. 3.2. About 3.20. Okay. Now, to kind of finish this off, okay, let's think about what was done here. This is about finding the physical meaning of slope, right? So in math class, back in well, actually 7th grade math to be certain, but definitely in math course 1, IM1, we learned about slope-intercept form of a line. And so y equals mx plus b. Go ahead and write that down. And then what we'll do is we're going to section this off with a chart that breaks this down into different parts. Okay, now on the y-axis, we had circumference. On the x-axis, we had diameter. And if you look, our y-intercept is virtually 0. I mean, it does have a value. In this case, it would be 1 plus 1, but it's pretty close to 0. So I'm going to go ahead and neglect the y-intercept for this particular example. Sometimes the y-intercept is crystal clear and has actual physical meaning. For this particular lesson, not so much. Now, what are we missing here? Well, if you look at this right here, what constant connects the circumference, the distance around a circle, to its diameter? Well, ladies and gentlemen, in my case, it's 3.2, but what is it really? It's pi, right? Pi is the ratio of a circle's circumference to its diameter. So ultimately, what is this right here? What I can state is 3.2 is my experimental approximation for pi, right? Which is the ratio of the circumference to the diameter. All right, so that's how we finish it out. Now, one final step, okay, is to do what's called an error analysis calculation. You just do that wherever you have room, okay, if you have it on the bottom. So we'll call this kind of a part 6. Error analysis, okay, specifically a percent error, right? So if I'm going to do a percent error on this to see basically how accurate am I, okay? It's the actual value minus your experimental value. And I'm putting vertical lines here because it's the absolute value of. And if you recall from IM1, the absolute value of any number is always positive, right? Divided by the actual value times 100. So if we do my example here, my percent error would be the actual value of pi, which is estimated 3.14 to 3 digits, minus my value, which I got 3.2. Okay. Subtract those two and make it positive. Absolute value bars make it positive. And then divide that by 3.14. Right? Times 100. So if we do that, we get 3.14 minus 3.2 is a negative 0.06. Divided that by 3.14 times 100, and I have about a 1.9% error. Okay, so that's about 1.9% error, which is pretty darn good, right? That means my data taking was pretty accurate, pretty spot on. And so percent error just kind of gives you that quantification of how careful you took your data and how accurate it actually was. All right. I hope you found this tutorial to be helpful in terms of the data graph construction of the data, and the data processing, meaning the slope calculation and developing meaning from that. All right.